Hello everyone. In this lecture, we will talk about how to do the numerical modeling of groundwater flow in two-dimensional system. So I here briefly prepared the schematic of the two-dimensional grid mesh system here. So let's say we have, I will, as we did in the one-dimensional numerical modeling lecture, we will focus on a arbitrary cell I, but in this mesh system, the first cell is located here, the left top one, and the cell index is increasing in this way, and once it touches the bottom cell of this column, then it should be n. So this mesh system is n by n system. Then the next cell is here, n plus 1. And this goes to the last cell here, which is n square. And we will consider the similar boundary conditions as in the first the one-dimensional system, where the left boundary was the flux boundary, and the quantity is q bar, and we also here consider the head boundary on the right hand side, right boundary, as much as h bar. Then let's think about the arbitrary grid cell and adjacent cells like this. Then we should be able to number the adjacent cells. So considering the increasing order of the cell index, we will have here I minus 1 and here I plus 1. And be careful about these two cells, because between these two cells there are the in-between cells as many as n, because the size, the one directional size is n. So this cell should be numbered as I minus n. And similarly, this cell should be numbered as I plus n, right? And I forgot to mention the other boundary condition on the bottom and the top boundary, which is impermeable boundary condition. So let's begin with the first cell I, the arbitrary cell I. For cell I, we again start from the Reynolds equation and integrating that equation, and we will have, so first let's number or index the cells interfaces. So here this cell interface is L, standing for left, and this cell interface is R, standing for right, and this cell interface as U, standing for up, and this cell interface as D, standing for down. Then the two-dimensional version of the mass balance equation is written as minus T, sorry. So let's rewrite here. The mass balance equation can be written as minus QL minus QU plus QD plus QR is equal to 0. And this relationship should be satisfied for all grid cells. And I will start from cell I. So for cell I, we will have this equation, and we know how to express each Darcy flux at the interface using the transmissibility term. So this can be written as minus TL HI minus N minus HI. This is QL minus QL, and the QU should be written as minus TU times HI minus 1 minus HI, and the QD is written as plus TD times HI minus HI plus N 1 plus TL times HI minus HI plus N, right? This is equal to 0. And considering the final format that we will establish in terms of matrices, this equation can be written as minus TL times HI minus N minus this term TU HI minus 1 plus TL this term plus TU this term plus TD plus TR times HI, right? And there are two other terms, which is plus, no, or is minus TD times HI plus 1 minus TL times HI plus N is equal to 0. And if you remember the matrix equation that we established for one-dimensional system, you will understand this term, the TL plus TU plus TD plus TL. This term will be the diagonal element, and these two elements would be the off-diagonal elements. All right? So I will revisit this equation later when we have all set of equations describing the boundary conditions, and then we will establish the matrix equations. And so for the left boundary, the flux boundary cells. So for flux boundary cells, left or flux boundary cells, let's denote as flux boundary cells. Boundary cells. We have known term as Q bar, which is corresponding to QL, right? So this term will be gone, and that means this term will be gone. Then we can just need, and this will be replaced by minus Q bar, and that can be moved to the right hand side. So we will have only this term, and this term, and the Q bar on the right hand side, which can be written as, I will fully express these three terms as minus TU H minus TU HI minus 1 TD minus and the diagonal term TU plus TD plus TL times hi minus td times hi plus 1 minus tl hi plus n is equal to q bar, right? So this equation is the equation that will be implemented in the matrix multiplication format. However, we have two grid cells in this boundary cell, this boundary column, because they are having another boundary condition on the top for this one and on the bottom for this one, all right? So this equation will be maintained. However, for cell I1, we have the no flux boundary here. So that is corresponding to the U term, the U boundary, which is corresponding to TU HI minus 1. So I will cancel this TU HI minus 1 and this term TU. So it can be rewritten as this is cancelled and this is cancelled. So we have TD plus TL times HI minus TD HI plus 1 minus and TL HI plus N is equal to Q bar, right? And for cell IN, which is this cell, we will cancel the down term, the down boundary interface term, which is corresponding to here. So we will have this equation, but we need to cancel this one and this one. So we will have minus TU HI minus 1 plus TU plus TL HI minus TD HI plus 1 minus TL HI plus N is equal to Q bar, right? So for these boundary cells, we have this equation, but for the first and the last cell, we have this equation and this equation. And all of these should be implemented in the matrix multiplication format. And let's move on to the head boundary cells. So for head boundary cells, we have this equation again, but we have to consider the head boundary condition, which is corresponding to this term HI plus N, right? So we will cancel this term and replace it with H bar, and the TL multiplied by the H bar term will be moved to the right hand side because it is constant, and the other terms will be remained in this equation. So we can have minus TL HI minus N minus TU HI minus 1 plus TL plus TU plus TD plus TL, right? Times HI, and the TD term minus TD HI plus 1, and then the minus TL times HI plus N is replaced by minus TL H bar, which will be moved to the right hand side. So we can write down like TR times H bar. So this is the general discrete equation for this head boundary cells. But again, we have this n square and n square minus m plus 1 cell. So it can be written as like this because we have n grid cells, and so if we just deduct n from this n square, then the corresponding cell would be this one. So we should have a plus 1 term here. So these two cells have another additional boundary conditions, which is impermeable boundary on the top, the upper interface for this cell, and the down interface for this last cell. So we will write down those for those cells. For cell n square minus n plus 1. We have again here this equation will be used, but we need to cancel out the upper term, the u up interface term. So we will have minus TL HI minus N, and this will be gone, and this is gone, and we have this one as a remaining. Then we have T so plus TL plus TD plus TL HI minus TD HI plus 1 is equal to TL H bar. And for the last cell, n square, we have to still, again, we have to use this equation, but canceling out the down term, TD. So we have minus TL HI minus N minus TU HI minus 1 plus TL plus TU plus TL HI minus the down term is cancelled, right? So we don't have to write this equation, and this equation is equal to TL H bar. Yes. So we are done with this left and right boundary cells. And the remaining cells that we have to consider is this impermeable boundary cells, where it covers like this and covers like this. So I will start with this upper impermeable boundary cells. So for the top impermeable cells, we still use this full equation, but we need to cancel out the upper interface cells, which is corresponding to this. So then the top impermeable cells will be expressed by like minus TL HI minus N minus TU times H minus 1 plus TL plus TU. Sorry, so I said this should be cancelled out. So it should be here. So plus T L plus TD plus TL times HI, and then this term, down interface term, minus TD HI plus 1 minus TL HI plus N is equal to 0, right? And for the bottom impermeable cells, for bottom impermeable cells, we have this equation again, but in this time we have to cancel this term, the down interface term. So we have minus TL HI minus N minus TU HI minus 1 plus TL plus TU plus TL times HI minus this term TL HI plus N is equal to 0. So we have now all equations expressing all grid cells, and we can formulate the matrix multiplication equation. By solving that equation, we can solve the whole head distribution over the whole grid cells here. So I draw here the matrix equation. Only for I here just draw the transmissibility matrix, and I will show how we can implement this equation into this matrix form. So first of all, let's start with the cell I here. Then this equation can be, as we covered in previously, this can be written as minus T L H I minus N plus minus T U H I minus 1 plus T L plus T U plus T D plus T L times H I minus T D H I plus 1 minus T L H I plus N is equal to 0. And for cell I, the center diagonal term would be this one. Right? And the one off diagonal term here is T minus TU, and the on off diagonal term here would be minus TD. And we have TL here, and this is corresponding to HI, and this is corresponding to HI minus 1. And this TL term should be located where the location is corresponding to the HI minus N, that is here, HL, TL, and the span between this term and up to this diagonal term would be N, right? And here we have another off-diagonal term away by another N here, and that is TR. Minus TR. And we should implement the other non-zero values considering the boundary conditions. And we have to also write the head boundary vector. So that will be here the head vector and the right hand side column vector. And the elements should be here hi, hi minus 1, hi plus 1, down to hn square, and here are h1. And this is the right hand side vector. And most of the elements are 0, but there should be, you should be able to know where the elements are non-zero and what is the value for those non-zero elements. And we will also cover this material in the in-person lecture. Thank you very much.